Section 2.7, Defining the Derivative. The objectives of this section are to compute an average rate of change and to find a simplified difference quotient, and finally define the derivative at a point as a limit of a difference quotient. So we begin with the average rate of change. And this is just a fancy way of saying the slope of a secant line, but we're using calculus language. So instead of calling it the slope of a secant line, we will be calling it the average rate of change. So what do I want you to imagine here? I want you to imagine that there is a function f of x, that's this guy in blue over here, and there's a couple points on this function that you select. In this particular instant, I'm calling the first one a on the x-axis and b. So randomly choose the numbers a and b. Sometimes they're going to be 1 and 5, maybe they're 0 and 10, maybe they're 5 and -4. Who knows, who cares, but we're just going to call them a and b. Each one of these x coordinates will line up with the graph at the function f of x, and it will give us f of a and f of b on the y-axis. So each one of the x coordinates will have a y coordinate, and we're calling them f of a and f of b. When I ask for the average rate of change, I want you to think about the slope of that red line that connects the 2 points a and b. And in general, the slope of any line, we know from algebra, it's the y2 minus the y1 over x2 minus x1. So if I just pause here for a second and calculate the slope of this dotted line, which is now what we're calling average rate of change, what would my slope look like? So the y2 is basically the y coordinate of the second number, that's basically f of b. So I'm going to write f of b first, minus the y1. And what is exactly y1? Y1 is the y coordinate of the first point. That's what I'm going to be putting next on the numerator. So this is going to be f of a. And then finally, x2 minus x1. These are just the b and the a. The second one is b, so I put it first. And x1 is the first point, which is a. And this definition is what you're seeing over in the small theorem in the little box. So this is one way to describe the slope of the secant line. And remember, it's called secant because it's touching the function in two different locations. That's the technical name we use. Now, the second definition here gives us a slightly different format to describe the slope of the secant line. And let me describe how to get that second definition. So first of all, instead of a and b, instead of all these numbers, what I'm going to start by doing is I'm going to call my first guy with the same letter a, and I'm going to say leave some distance between a and the second point. That distance, I'm going to be calling it h. So h is just some random number which represents a distance. And if it's a distance, then the second point will be just simply a plus h, because I'm adding h to the number a, and that's how I get my second point. Now, the first point is still going to be called a and f of a, because the y-coordinate will be what happens when I plug in a into the function f of x, and that's what we're calling f of a. The second point, though, it's not going to be called b and f of b anymore. It's going to be called a plus h, because that's its x-coordinate, and its y-coordinate will be f of a plus h. So in other terms, the y-axis is going to have f of a plus h there. And again, my slope is y2 minus y1. So let's write it down. It's the y2 minus y1 over x2 minus x1. This is the slope of any line in general. And so in my problem, what is the y2? The y2 is the y-coordinate of the second point. Remember, that's this guy over here, also known as f of a plus h. That is going to be the y2, so I'm going to write f of a plus h on the numerator. And then I need to subtract from it the y-coordinate of the first point. The first point is the a point. Its y-coordinate is f of a. And so I need to put that guy next on the numerator in order to get the slope of the line. So f of a goes next. And on the denominator, it's the x2 minus x1. So what exactly is x2? It's that number right there. So I don't know what it is right now because we don't have specific values, but I just know it's called a plus h. And finally, I need to subtract from all this the x1. And what is x1 exactly? x1 is the starting point In this case, I'm just calling it A. And if you notice, the denominator has now A plus H minus A. So instead of A plus H minus A, I could just write down just H, because A minus A will cancel out, and I just get H on the denominator, and that's how they're getting this second formula over here. It's just a different way of representing the slope of the same line. And by the way, that's going to be called the difference quotient. This is going to be called the difference quotient, and later on, I'm going to be putting a limit in front of it, and that's what we're going to be calling the derivative when we get there. So that's going to be our third goal in this section. But I just want you to realize that what we just did is basically describe the slope of a line. Instead of using algebra notation, we're using fancy calculus notation. So let's see how this is going to work in practice and how do you calculate the average rate of change. So example number 1 is giving us some kind of story. It says the average cost of owning and operating a car in the US is approximated by this function C of t, where C of t is measured in cents per mile and t is measured in years, with t0 corresponding to the year 2010. So 2010 is year 0, for example. So that means if you want to calculate the average cost of operating the vehicle or the car, you put 0 into this equation. But if you want to know, for example, the cost at 2015, then you have to say, okay, 2015 is 5 years after 2010, so I would have to plug in 5 into this equation to get the cost of operating my vehicle or my car. All right, so with that in mind, the first problem is asking me for the graph or the sketch of the function. So sketch of the function just means tell me, approximately what the graph of the C of t looks like. It doesn't have to be perfect, just has to look like the graph of some kind of function. And in this case, this is a quadratic because the t has power 2. So I'm expecting to see a parabola when I graph this thing. And I think the best way to graph it is to just use our TI calculator. So let's turn it on and put this equation into the TI calculator. So to graph it, I'm just going to click on Y. And remember, I don't have the letter T on my calculator. I'm just going to use X for everything. So 0.2x squared, and then 0.42x, and finally plus 19.2. That's the provided equation. I'm using X because I don't have the letter T on my screen. And when I do this, I want the window to match what's on paper, so it's easy to copy the graph. And approximately the x minimum is going to be 0. The x maximum is going to be 12. On paper, it looks like it's 12.5, but I think 12 is good to go. The y minimum, it seems like they want us to start at 0, and y maximum, the graph goes up to 50, but maybe slightly higher, but I'm going to stop at 50. And let's click on graph, and there you go. You see it looks sort of like a parabola. It's not a straight line. And so we need to transfer this from the calculator screen to our paper. And to do that, we're just going to click on trace and just trace a few points. For example, 0 gives me 19.2. If I trace 5, for instance, I'm going to get 26.3. If I trace 10, for instance, I'm going to get 43.4. So use these points to plot a sketch of the parabola. So again, the numbers I'm going to be using are 0, which gives me 19.2, 5, which gives me 26.3, and then 10, which gives me approximately 43.4. I'll transfer them to the paper and then connect the dots to get the graph of the parabola. So I recorded the numbers for you so you can see which numbers I used. So at 0, I got 19.2. At 5, we got 26.3. And at 10, we got 43.4. And it doesn't have to be perfect. Again, like I said, it just has to look like a parabola. So just make sure it's not a straight line. And we're roughly estimating where the points land. And that's what we're getting. We're getting a low parabola. Okay, so now that we've done this part, let's move on to part 2, which is the question that says, what was the cost of owning and operating a car in 2010 and then again in 2015? So what exactly are they asking me here? They're basically saying they want me to plug some random number into the given equation. And remember, 2010 represents the initial starting point for us, which means that time there is going to be 0. And we just discovered by tracing that the number will be 19.2. And remember, this is cents per mile. So you can either write it like cents and then little fraction sign with mile underneath it, or you can write cents per mile with actual letters. So that's the cost at 2010, and what is the cost in 2015? So I'm going to have to do something similar. I'm going to have to say that the cost of operating the vehicle in 2015 is C of some random number, and in this case, 2015 is 5 years after 2010, and remember 2010 is our initial starting point, and we know that the cost of operating the vehicle at C5, when time is 5, was 26.3. So I'm just going to write 26.3, and again, the unit is cents per mile. And that is the end of this second part of the problem. Okay, so for part 3, it's asking us for the average rate of change. So I'm going to write average rate of change. And this is pretty much just the slope of a secant line. And which years are we comparing? We're comparing 2010 and 2015. And remember, 2010 for us represents the year when time is equal to 0. So 2015 is time equal to 5. So just like we said before, this is just y2 minus y1 over x2 minus x1, except I have to use calculus notation. So I have to write something like c of 5 minus c of 0 divided by 5 minus 0. So I'm using the first definition that was provided in the little box. And we have found all these numbers, by the way, so I just have to copy them. The first one is 26.3, then subtract 19.2, and divide it all by 5, because 5 minus 0 is just 5. And what's the answer? So putting in the calculator, just be careful because you'll need parentheses around the numerator, but my answer is 1.42. So I'm going to write 1.42, and the unit, if you care, it's cents per mile, and the denominator here represents years, and so this is per year. So it's a weird, funky looking unit, but it's the bottom line is the number is 1.42. So what is that number? What does it represent? So if I go back to my graph real quick, and I'd graph the dotted line going from year 5 to year 10, that would be this line basically. And what we're saying is that the slope of this line is the number we just found. And we just found the number to be 1.42. So this line here that connects year 5 to year 10 has a slope that is 1.42. That's the meaning of the rate of change from the year 2015 to the year 2020. Sorry, I think I jumped the gun. It's actually not this line. It's the line that connects the year 0 to the year 5. It's this line over here whose slope we just found, not the other one. The other one we're going to find in a couple of minutes. So this is the line that we care about. The year 2010 is the starting year, and the year 2015 is the middle one. And we discovered that the slope was 1.42. I'm sorry about that. I apologize for any confusion. The other line that connects these 2 points is going to be next, and I kind of jumped ahead in my head. Anyway, that's the slope of that line, so let's continue and now talk about the next part of the question, which is, looking at the graph, where do you think the cost is increasing faster, in year 2015 or in year 2020? So what exactly do they want me to do here? So looking back at the graph, the year 2015 is down here, and the year 2020 is basically this one over here. It's 10 years after. So there are some lines that we will graph, and let me make them in different colors so we can see them a little bit better. So the first one I'll graph in blue. So there's a line at this location here. Let me erase the other one since I don't need it anymore. And there's another graph of a line over here that's tangent to the graph. Basically, what they're asking me right now is, without using any math whatsoever, to estimate whether the slope of this line at this location when time is 5 is bigger or smaller than the slope of this line at this location when time is equal to 10. And just by kind of carefully looking at it, I feel like this slope here is a little bit larger because the line is steeper. So I think the increase is faster in the second year, which is 2020. So let's go ahead and write that down. We think that the cost of operating a car was increasing faster in the 2020 year. Now later on, to prove this, we will actually find the derivative at 2015 and 2020 and compare the numbers. But for now, just by kind of estimating, by looking at the graph and using our intuition, we can kind of decide that the second line is steeper than the first one. So the cost of operating a car was probably increasing faster in 2020. So this is now, for now, like a theory or like a hypothesis, but later on we can use derivatives to actually evaluate and confirm our understanding. So for the last part of this problem, they want me to find the average rate of change in the cost of operating a car from 2015 to 2020. So again, remember 2015 is 5 years after 2010, and this guy here is going to be 10 years after 2010. So the average rate of change is going to be, again, some kind of slope of some secant line. And instead of using y2 minus y1 and x2 minus x1, I have to write using calculus notation. So this is c of 10 minus c of 5 divided by 10 minus 5 themselves. And so that's the slope of the secant line that connects the 2 points. When I said earlier I jumped ahead, I was talking about the line that connects these 2 points, and this is the line that we care about now. So we want to know its slope. And we have already calculated some numbers to help us with this task. So let's go ahead and put it all together. So C of 10, we know from earlier when we traced this on the calculator, we got 43.4. And we know that C of 5 is 26.3. And I know 10 minus 5 is just simply 5. So remember, this number is just the y-coordinate when I put 10 into my equation, and I didn't calculate it by hand. I just used the trace. This is the y-coordinate. The 26.3 is the y-coordinate that you get when you plug in 5 into the given equation. And again, I use the trace command to find it. And now I just need to evaluate this using my calculator. So let's go ahead and punch it in and see what kind of solution we're going to get. So let's go to our calculator screen. And again, I'm going to first start by putting some parentheses, then 43.4 minus 26.3, and divide it all by the 5 on the denominator. Again, make sure parentheses at the beginning and end of the numerator, because otherwise the calculator will misunderstand what you're doing and it will only divide the 26 by the 5, not the whole numerator. In any case, right now the answer is 3.42. So 3.42, and the unit is cents per mile. That's the numerator because that represents the cost. And the denominator is in years, so cents per mile per year is my final unit. So 3.42 is the number that we care about. So again, in example number 2, we're going to find the average rate of change, but the function here is different. It's x squared minus 5x. And actually, we're going to use the 2 different definitions of the average rate of change in this problem, but let's begin with the simple one. So first, I'm being told to find the average rate of change from 1 to 2. So average rate of change. And so I will write something like it's going to be f of the second point minus f of the first point divided by the second point minus the first point. So it's f of 2 minus f of 1 divided by 2 minus 1. And let's just go on a scratch paper and calculate all of these values. So what is f of 2 going to be? What is f of 1 going to be? So I'm not going to graph this with my calculator and use the calculator to help me out. I'll just do everything by hand here so you can see it's not terribly difficult. So the function f of x is x squared minus 5x. So instead of writing x's, I put parentheses. Then I put 2 into all the parentheses because that's the number that I'm trying to calculate the y-coordinate of. And that's going to be 4 minus 10, which is going to be negative 6. So the first number that I place on the numerator is going to be negative 6. That's going to be the first number. And the second number is going to be f of 1. So again, x squared minus 5 times x. But this time I'm plugging in 1. 1 squared is 1. 5 times 1 is 5. And the solution there is negative 4. So the second number I put in is going to be negative 4. But be careful, it has a minus already in the formula. So let's see. Putting all this together, I'm going to get negative 6 minus a negative 4 divided by 2 minus 1. And rather than writing 2 minus 1, I'll just write 1 because 2 minus 1 is, in fact, equal to 1. So remember, these are the values we calculated by hand. In the previous problem, we used the trace command to find them. Regardless of how you find them, the answer should be always true. So negative 6 plus 4 divided by 1 is just negative 6 plus 4, which is ultimately just simply negative 2. So my final answer for the average rate of change of this function is negative 2. Okay, so that's the end of part 1. And now for part 2, they want me to do the same thing again. So let me just record the function. The f of x we're working with is x squared minus 5x. So for this function, right, the one that's provided up here in the question, they want me to find the rate of change going from 1 to 1 plus h. So some distance away from 1, that's what the h stands for. So again, to find the average rate of change, I'm going to set up the same formula. So average rate of change, and instead of using the y2 minus y1, again, I have to stick with the calculus notation. And again, I have to say that it's f of the second point, and in this case, the second point is 1 plus h, minus f of the first point, which is 1, divided by the second point's coordinates, which are these, 1 plus h, minus the first point's coordinate, which is 1. And so it's slightly more tricky because my numerator now is going to be a little bit more complicated. I have to find f of 1 plus h over here on the numerator. So let's go to our scratch paper and find f of 1 plus h. So to find it, that just means I got to plug in 1 plus h everywhere I see an x. And so I'm going to get 1 plus h squared minus 5 times 1 plus h. And I'm going to FOIL this quickly. 1 plus h, all of it squared, is going to give me 1 plus 2h plus h squared. I'm using a rule to FOIL it fast, but if you don't know the rule, just write 1 plus h and then write it again, 1 plus h, and then multiply, multiply, FOIL as usual, and you should get the same result, 1 plus 2h plus h squared. I'm using a formula to do this. Next, I got to multiply the 5 times 1 and 5 times h, so I'm going to end up with 5 minus 5h. And I don't think there's any like terms except for 1 and negative 5, so let's just combine those two and leave everything else alone. And actually, there is 2h here and negative 5h, so I take it back. There are other like terms. So let's combine everybody. H squared first. 2h minus 5h is going to be negative 3h, and finally negative 5 plus 1 will give me negative 4. So this is the result of adding the constants, and this is the result of adding the h terms. So that's the numerator's first term. So all of these guys will be placed first, and next I need to place f of 1. So what exactly is f of 1? That just means put 1 into the function f of x. And so if I put 1 into the function f of x, I get 1 minus 5, which is going to give me negative 4. So that's the second number that I should be putting in my numerator. And be careful, it's negative, and the formula already has a minus sign, so double or put parentheses just so that you could be careful and not mess it up. Okay, I'm going to make this slightly smaller so we can fit everything here together. I'll put it on the side. So, okay, now we're ready to find the average rate of change. So first, h squared minus 3h minus 4. That's all the blue things that we calculated. We have a minus sign that's given to us by the formula. And then we have to put an extra negative 4 because that represents the f of 1. Now on the denominator, I have 1 plus h minus 1, and the 1s are going to cancel out. So I just get h. And that's where that formula in the table or in the theorem comes from. It's basically exactly this. Okay, first, let's go ahead and get rid of some of these parentheses. Here, there's a double negative, so we need to be careful. And write down h squared minus 3h minus 4. The double negative becomes a plus 4, all divided by h. And I can see that the 4s are not needed because one of them is positive and one of them is negative. So I'm going to write h squared minus 3h, all divided by h. And actually, what I'm seeing also is that the numerator has a couple of h's, so let's factor out an h term. And that leaves us with h minus 3, all divided by h. And since there's a repeating h on the numerator and the denominator, I'm going to cancel it, and the ones don't necessarily have to be written, because 1 times h minus 3 is going to be h minus 3, and divided by 1 is just simply another h minus 3. So that's the answer of the average rate of change. And by the way, when it's written with all these h's, we call it the difference quotient. So, the different name for the same thing. So either average rate of change, or when the letter h is present, we will just say it's the difference quotient. Okay, so with that in mind, we're going to continue to example 3 and see this difference quotient again, but for slightly more complicated functions. So in problem 3, the given function is 2 divided by x, so there's going to be a little bit more work involved here. And it's not terribly difficult. We're going to have to follow the same patterns that we just did to find the difference quotient. Okay, so I'm going to call it average rate of change or difference quotient, and the idea is basically the same. I'm given 2 points, and I want to find the slope of the secant line. So as usual, instead of using my algebra notation and writing y2 minus y1, I'm going to write first f of 3 plus h, because that's the y-coordinate of the second point, minus y1, but instead of y1, I'll write f of 3, because that's the coordinate of the first point. And then I need x2 minus x1, but instead of writing those, I'm going to write the coordinates of the second point, 3 plus h, minus the coordinate of the first point, which is 3. And you know what? Since I can see already that the 3's are going to cancel out, let's just not write them down at all. Let's just put h on the denominator instead of 3 plus h minus 3. And so when it's written in this form, I don't necessarily have to call it average rate of change anymore. I can call it now difference quotient. Okay, so let's calculate the f of 3 plus h f of 3 and divide everything by h. I think I'm going to need more space, so let me create an empty page and put everything on it. Okay, so keeping in mind that the function is 2 over x, let's find f of 3 plus h. So how does it work? I write the numerator 2, and every time I see an x term, I skip it and I write 3 plus h instead. And actually, that is the end of that one, that we're completely done with the first part. And remember, this is what I usually color in blue. And just as a reminder, this quantity, it needs to go first instead of all of the f of 3 and the h. So next, I need to calculate f of 3. And so what exactly is f of 3? So for f3, I need to plug 3 into the function every time I see an x. So this is it, 2 over 3. Literally, that's the end of that part, and this is the yellow portion, which is going to be going next. Okay, so I don't think this space here is enough, so let's continue on the other page. So the difference quotient, or the average rate of change. So for me, the numbers were 2 divided by 3 plus h for the first one. And then there's a minus sign that I need to write down because the formula comes with the minus. And then 2 over 3. So this guy is the blue quantity, the 2 over 3 plus h is the blue quantity, and the yellow quantity is 2 over 3. And it's all being divided by h. Okay, great. This is not the final answer because we need to simplify it. That's the purpose of this whole problem, is to learn how to simplify these expressions. And remember, I'm going to put the invisible one under the h, and we've dealt with problems like this before. This is what's known as a complex fraction. And to simplify it, you'll have to multiply all the fractions by a special quantity known as the LCD. In this case, the LCD is going to consist of the denominators that we see, which are 3 times 3 plus h, and I'm not going to write times 1 because it doesn't change anything. So what I'm going to do is give each one of these 3 fractions that in its numerator. So I'm going to continue here, and I'm going to say that first, the 2 over 3 plus h is going to get an LCD on top, 3 plus h. Then there's a negative 2/3 that is also going to get a 3 and 3 plus h on its numerator. And finally, the h that's already on the denominator is also going to get 3 and 3 plus h. So as long as I multiply every fraction by the LCD, this is consistent and it's valid, and we can simplify the expression by doing all this work. So this is supposed to be a quick, fast way of getting the solution and simplifying the complex fraction. And when you do this right, the fractions should disappear because you're multiplying by the LCD. So for the first part, the 3 plus h's are going to go away, and you're going to be left with some random numbers that you need to multiply and divide. So in this case, 2 times 3 times 1 over 1, the total there is just going to be 6. Then I'm going to write down my minus sign in the middle as usual. For the second fraction, what cancels out are the 3's. They become 1 and 1. And so what's left from all that mess is 2 times 3 plus h at the end. The extra ones are not going to contribute very much to anything. And down on the denominator, nothing cancels out. I'm just going to write 3h and then 3 plus h. So I'm not going to distribute anything down on the denominator yet, because typically what happens is some random numbers will cancel out in the process. So that's why I leave it in the factored form. Okay, what I gotta do next is take the -2 and distribute it to this parentheses. So when I do that, it's going to be 6 minus 2 times 3 is also 6. And then -2 times h is just -2h. On the denominator, nothing is happening. Like I said, don't FOIL it yet, because look what's going to happen next. First of all, the 6 and -6 are not needed. They're just going to disappear. They're just going to go away because one is positive and one is negative. And I'm going to end up with -2h. And by the way, there's a multiplication in the middle there. And on the denominator, I have 3 times h, technically, times 3 plus h. So I haven't been writing the little dots because it's understood that there's multiplication there. But I made them show up just to convince you that I can now cancel out the h's. Since it's a product, we can reduce it to lowest terms. And the final answer is going to be -2 divided by 3, and then again 3 plus h. So this is the final answer to my difference quotient for the function that's given to us. So like I said, later on I'm going to ask you for the derivative, and you will have to do all these steps that we just did, but once you get to here, there's one extra step that you do where you replace h with 0. And if I were to do that right now, I would get -2 over 9, and that would be called the derivative, basically. For now, though, let's not worry about it. We're not there yet. That's going to be an objective that will come in a few minutes. So again, we're going to find the difference quotient in example 4, and then yet again, the function is complicated a little bit because it's square root of x. So as usual, I'm not going to use the algebra notation. I'm going to write f of the second point minus f of the first point, and the second point in this case is 2 plus h minus f of the first point. The first point is just simply 2. And then I have to subtract this minus this on the denominator. So 2 plus h minus 2. And you know what? Again, I'm not going to worry about writing the 2's. I'm just going to put h because 2 minus 2 will be 0. The function I'm dealing with is the square root of x, so I can calculate this quickly in my head. First, for f of 2 plus h, put 2 plus h everywhere you see an x. So I'm going to end up with just 2 plus h inside of a radical. Then I need to calculate f of 2. So put 2 into this thing everywhere you see an x. So that's going to be just square root of 2, all divided by h. So that's technically the end, except it's not simplified. We want to be able to simplify it because later on we'll be putting a limit in front of it, and it won't work if it's in this form. So I'm going to continue, and what I'm noticing here is that my numerator has a bunch of radicals. So to treat it, I'm going to multiply by the conjugate, and the conjugate is the square root of 2 plus h plus the square root of 2. And then whatever you do on the numerator, you have to do the same thing on the denominator. So this is how you deal with the scenarios where you have square roots. You just multiply the original problem by a special version of 1. Technically, this is just a special version of 1 because everything can be canceled out, and 1 over 1 is really 1. And we always pick the conjugate because that creates a pattern for us on the numerator. The pattern is that this guy is like an A, this guy is like a B, and then it's again A, and then again B. But one time it's A minus B, the other time it's A plus B, which is a squared minus b squared. That's the idea, and then we can kind of FOIL everything quickly and calculate the differences and add them up very, very fast. So in my case here, when I multiply the a minus b with the a plus b, what's going to end up happening is I'm going to end up with 2 plus h, all of it squared, minus the square root of 2, all of it squared. That's technically what I'm supposed to do because my formula says to square the bases and then subtract them. This is known as the difference of squares formula. On the denominator, for now, let's not FOIL anything. Let's just leave it alone because technically what's going to end up happening is it's going to end up reducing by itself. So we don't want to FOIL it because then we won't see that it's possible to reduce the fraction to lowest terms. Okay, so now let's begin by squaring the numerator terms. So the square root of 2 plus h squared is just going to be 2 plus h minus, so remember this minus comes from the formula. It's just been carrying along all the way, and then it became a difference of 2 squares, and that's where the new minus is coming from. And now the square root of 2 squared is just 2. And again, the denominator, we just copy it as is. We're not going to change the denominator right now. Okay, so I'm seeing a 2 minus 2 on top, so I'm going to get rid of them. And what I end up with is just h on the numerator, all divided by h, again, times 2 plus h plus the square root of 2 on the denominator. And finally, there's a product between the denominator terms, so we can now reduce everything to lowest terms. And the final answer so far is just 1 on top, and 2 plus h on the bottom, plus another square root of 2 on the bottom. So this is it for now, but in a second or a few minutes, we're going to be doing this whole process again. But like I said, we're going to be putting an extra step in front. We're going to be putting a limit as h approaches 0. So when we get to this box, it won't be the answer because we'll be required to put 0 into all the h's that we see to get what's known as the derivative. So the derivative requires doing an extra step that we're not doing yet, which is replacing h with 0. Then you always get some random number, and that's going to be called the derivative. Okay, so speaking of the derivative, here it is. This is the formal definition of the derivative. And as you can see, these formulas right here in the middle of the page are exactly what we've been talking about. It's the secant line's slope, but what we're doing to it is we're putting a limit in front of it, and that's creating what's known as the derivative. And in this table, we're defining the derivative at a specific point, but in the future, we're going to be finding the derivative equation. So meaning we're going to get some kind of equation that gives us the derivative at any random point in general, and that's more useful than finding the derivative at a point specifically. But basically, the idea behind what we're doing here and the reason why you're seeing limits in front of everybody is the following. So let's go back a few pages to the start of this section. When we started this section, we had a function and we had some 2 random points on this graph, and we connected the dots to each other. Now, the idea is this. We want to know the slope of the tangent line. The tangent line is a line right here that touches the curve barely once at the point x equal to a. So we care about what's happening at a. This is where we're focusing all of our attention. We want to know the slope of a line that we're calling the tangent line. And by definition, because it's called tangent, it touches the curve only once at that moment called x equal to a. So because we only have one point, the formula that we normally use, which is y2 minus y1 over x2 minus x1, is basically useless. We don't have a second point to think of, right? By definition, the line is touching the curve only once. So how can we get the slope of this line, called the tangent line, if we don't have a second point? And the idea is basically this. What you should do is take this point B and just slide it as close as possible to the point A. So it's kind of like cheating a little bit. You're creating your own second point and you're sliding it as close as possible to A, to the point where it's not even distinguishable from A. The difference between the first point and the second point is so small that it's almost 0. So that's where we're getting the limit as x approaches a of x minus a, f of x minus f of a over x minus a, or the other definition, which was the limit as h approaches 0 with f of a plus h minus f of a over h. So by doing this, by putting the space between the points, which we're calling h, by making that approach 0, we're saying it's going to be so tiny that you can't even see the space. You get 2 points basically, and then you can kind of graph the line and find its slope. That's sort of the idea that's happening behind the scenes. And the process of sliding the point, which is here now, closer and closer to A, to the point where they're indistinguishable and they're kind of on top of each other, that process to slide it, it uses the limits concept. So that's how we're getting the definition of the limit at a specific point, x equal A. So it sounds complicated, but actually it's not that bad because we've pretty much done everything we need to do in order for you to find the slope of a tangent line. And so let's kind of look at it and see how it would be done for example 5. So first of all, there's a new notation now. It's this f apostrophe. So f apostrophe 3, that references the derivative. So the function itself is known as f of x. F of 3 would be the y coordinate when x is equal to 3 on the function f of x. Whereas f prime, so that's how we pronounce that apostrophe, f apostrophe 3, is no longer the y coordinate. F prime of 3 is the slope of a tangent line that the curve has, the function f of x has, when x equals to 3. So it's slightly complicated, and there's a lot of words I understand, but you're going to get so familiar with this, and it's going to be a piece of cake later on. Now, we can also call this the instantaneous rate of change instead of the derivative. So those words are kind of interchangeable. So if you hear the word derivative or instantaneous rate of change, you should know they're both the same thing. They involve doing this difference quotient thing and then putting a limit in front of it. Or if you prefer the other definition with the limit in front of it, it doesn't matter. Either way, it's perfectly acceptable. So with that in mind, let's take a look at example 5, which gives us a function, and it's asking us to find f prime of 3 using the first definition of the derivative. So they want me to find the derivative using this definition, the first one in the box. Okay, so let's see. First of all, f prime of 3. So I'm being told in the formula that I'm supposed to put the limit as x approaches a. So what exactly is a in my problem? In my problem, because I'm seeing 3 inside the parentheses there, that means that a is going to be 3 for us. So the limit as x approaches 3, and then I'm supposed to write a fraction where I put f of x first, so this is the equation of the function that we're given, minus f of a, and remember a for us is 3, because that's the number that we see inside the parentheses. And finally, on the denominator, we have x minus a again, but then again, a is 3 because that's the number inside the parentheses. So this definition will not work if I don't give you an a. And how do I give you the a? I either say it in words, here's the a, find the derivative at it, or I just say find f apostrophe of 3, and you'll know that the a I'm talking about is equal to 3. So those are the only ways I can give you the a. Okay, so that's the first definition. So let's see how this works. So first, I'm going to write the limit as x approaches 3. And next, they want me to write down f of x. So what is f of x in this problem? It's the given function. So just write that equation first. So in this case, I'm going to write 2 over x. Then there's a minus sign. Sorry about that. So there's a minus sign next. So we're going to put minus next. Then they want me to write f of 3. So what is f of 3? F of 3 is the number I get when I put 3 into this function. And so think about it. When I put 3 into the function, I'm going to see 2/3 because there's only one x in the denominator and it needs to be replaced with 3. Okay, down on the denominator, nothing is changing for now. We're just going to put x minus 3. Okay, perfect. So this is the end of the setup. Now, this is a limit problem, and whenever we have limit, we usually try to punch in the number and see if it works by direct substitution. I guarantee you that if you try to do it now, you're going to have 0 over 0, and that's bad. We don't want 0 over 0 because that's not an answer. So let's not do direct substitution yet. Let's clean up this massive mess first, then use direct substitution. So how do I clean this? So first, I'm going to put the invisible 1 under the x minus 3. And now it kind of looks like we have 3 fractions. And we ask, what's the LCD? So what's the LCD? Let's write it over here. Let's write the LCD. So first I'm seeing x, then I'm seeing 3, and then I'm seeing 1. But 3x times 1 is just 3x. So I'm just going to write 3x, and that's my LCD. And what I'm supposed to do next is multiply every fraction on the top by the LCD to simplify the expression. So again, I'm writing f prime of 3, so I don't forget what I'm looking for. I'm looking for the derivative at 3, or the instantaneous rate of change for the function f of x at x equal to 3. So this is the slope of the tangent line when x equals 3. It is a limit as x approaches 3. And first, we'll have the 2 over x, and we're multiplying the top by 3x. Next, we have the 2 over 3, and we're multiplying the top by 3x also. Then finally, we have x minus 3, and I'm not going to write the invisible 1 anymore, and I'm multiplying the top by 3x. So this is, again, how we did it a few minutes ago, how we simplified the complex fraction, and that's how we do it every time. Okay, remember this minus in the middle is the one that came from the formula, and keep carrying it. Okay, so let's actually reduce everything to lowest terms. So for the first one, the only thing that's going to cancel there are the x's are going to disappear, and they're going to become 1 and 1. And when they become 1 and 1, the only thing that will be left is 2 times 3, which gives me 6. So 6 minus, that's the minus that we started with. And now for the second one, there's 2 times 3x divided by 3. The 3's are going to cancel out. And when the 3's cancel out, we just get 1's. And 2 times 1 times x divided by 1 is just simply going to be 2x. So 6 minus 2x. And down on the bottom, we just have 3x. I'll write it first. And then x minus 3. Okay, if I try to plug the 3 in right now into all this, nothing is going to work again. It's going to be 0 over 0. So again, continue reducing the fraction. So again, I'm writing f prime of 3, or f apostrophe of 3, so I don't forget what I'm doing in this whole problem and what's the purpose of this. And now I'm going to look at this fraction and think about how to reduce it to lowest terms. Well, it seems like it's a good idea to factor the numerator because the denominator is already factored. And I'm noticing that the 2 here is negative, and we don't like having our x, which is the 2x, with the negative. So I'm going to factor negative 2 out, and when I factor negative 2 out, that leaves me with basically x minus 3. So to double check it, you could just FOIL it out, and let's confirm. When I multiply negative 2 times x, I get negative 2x, perfect. And I multiply the negative 2 with the negative 3, I get the 6 that was already there, so that's perfect. So that's the factored version of the numerator, and we're doing all this because now we can finally get rid of the x minus 3's. And we're left with the limit as x approaches 3 of negative 2 on top and 3x on the bottom. So this is it. Let's finally try to do the direct substitution and plug in the limit, which is x approaching 3. And in this case, it's actually going to work. So f prime of 3 is going to be negative 2 divided by 3 times 3, because the limit has x approaching 3, and the answer is negative 2 over 9. And that's the derivative at the point 3. So to kind of help you understand what's going on with this whole thing, I'm going to graph the function on my calculator. So the blue graph is the graph of the function that we're given. And the red line is the tangent line when x equals 3. So let me just type in 3 here so you can see what we're looking at. So this is the function 2 over x. And at that location, the y-coordinate is 0.66 and so on and so forth. The function f of x has a tangent line at that location, and that tangent line is what you're seeing in red on your screen. We are investigating the slope of that line, and it turns out that the slope was some kind of random number, -2 over 9. The number itself is not that important. It's just understanding what it means is more important at this point in time. Later on, you'll get so quick at finding the slopes, and we will give you shortcuts to find it. But that line, the red one, is technically touching the curve only in one location, and at that location, it matches with the curve. So I'm going to click my down arrow to jump to the line from the function to the line. I can just trace the function itself or the line. So notice how the equation changes and the colors change on my screen. That's because I'm jumping from one function to the other one. But I want you to notice what's happening on the y-coordinate at the bottom of the screen. The y-coordinate right now is 0.666 and so on and so forth. That's basically 2/3. When I jump down and I go to the tangent line, the y-coordinate is the same. That's because the tangent line and the function are identical at that location when x is equal to 3. And technically, this line only touches the curve at that single location, but it doesn't touch the function anywhere else. On my calculator, the pixels are way too big, so I'm kind of seeing the overlap for a lot longer. But that is the tangent line we're talking about, by the way. Okay, so that's kind of the meaning of all of this that you just did. So there's a tangent line, you want its slope, so you have to find the limit of the difference quotient. Okay, so I'm going to produce this answer -2 over 9 again for you, but this time using the second definition of the derivative. And what do I mean by the second definition? I'm talking about this one over here, the limit with the a's and h's and everything else. So first, what I'm going to do is copy the function's name to my new page. So the function f of x is 2 over x. And again, investigate what the derivative is. So I'm looking for the f prime of 3, but I'm looking for it using the second definition, which is the limit as h approaches 0, and the numerator is f of the 3 plus h minus the f of 3, all divided by h. So again, the a in this problem is that 3 right there. And again, nobody's going to tell you this. You have to kind of know it to yourself, and then you have to replace it everywhere in the numerator. The difference between this one and the last problem is that here we have h under the limit, not x under the limit. So that's the major difference. But everything else is basically kind of the same. Okay, so first things first, let's write the limit every time until we actually plug in the h equal to 0. And this time I'm dealing with f of x. It's 2 over x, but what I want to find first is f of 3 plus h. So that means go to the function f of x, and every time you see an x, remove it and write 3 plus h instead. Next, I have f of 3, so I'm supposed to plug in 3 into the function every time I see an x, and I'm going to color that in yellow. So what do I get when I what do I get when I plug in 3? I get just simply 2/3. So the first one is 2 over 3 plus h, the second one is just 2 over 3, and that whole thing is divided by h. And I do believe that we did this earlier, actually, in a previous problem without knowing it. We calculated the difference quotient of this fraction. So if I rewind back a couple pages, you'll see that my function was the same, my a was the same, and we did all the math. So I won't rewrite all of these steps. I'll just copy the answer that we got over on this page. But the steps are already in the previous parts of this video if you want to look at them. But the bottom line is I'm going to grab the -2 plus, the -2 divided by 3 times 3 plus h. I'm going to basically literally copy, paste it onto my page over here. So my f prime of 3 is equal to the limit as h approaches 0, and I'm just going to paste the answer that we found previously. and I'm going to remove the box from around it. But the steps that would be here are on a previous page. So I scribbled that the steps are on a previous page, and now I'm ready to actually find the limit. This time my h is approaching 0, so I'm just going to replace that h with 0. And so what is f prime of 3 going to be? So it's no surprise to you that it's going to be negative 2 times 3 plus 0 instead of h. And 3 plus 0 is going to be 3. 3 times 3 is 9, and we get negative 2 over 9. The same exact solution that we had on the previous page. Obviously, they have to be the same. It's the same function and the same derivative at the same location. So it's the same line, so the slopes shouldn't change. The difference is just how you get to it. How you find it is slightly different. So from now on, you can use either method 1 or method 2 to find the equation, to find the derivative at any point. And each one of these methods has a slightly different, slightly better advantage or disadvantage. And you're going to develop your own preference as you work through the homework problems and decide which method is better for you. I feel like this method is better for me personally, especially in light of what's going to come in the future. So if you can, try to find the limit always using the H definition. That would be a little bit better for you later on in the sections that will be coming up. And okay, we get to example number 6, which is the big finale, kind of. This is the whole point of calculus. It's to find the equation of the line tangent to a function at a specific point. So earlier, I had this function, and as you can see, the y2 up on the top screen, I already have an equation written down. That's the equation of the line. I put it here in order to get the tangent line, actually. And you probably didn't know where that line came from, and you just kind of watched the video and you said, okay, cool. But how do you get this line, right? So how do you get the equation of the line? Well, that's what we're going to be doing in our problem. We're going to have a function and we want to know the equation of the tangent line. This is one of the two main reasons why calculus was invented. It's to investigate and to answer the question of what is the equation of the tangent line to a specific curve. And we are going to do that now with a pretty simple function called f of x equals to x squared. So the function f of x equal to x squared looks like a parabola. There's a place on the x-axis called x equal to 1. At that location, there's a y-coordinate and there's a tangent line. This is the tangent line whose equation we want to find. And so how do you find it? Well, we're going to use calculus for it because the line has only one point that we know of. We don't know a second point on the line, so we'll need derivatives and this new thing called f prime to get the slope of this function, or this line. And so we'll be able to graph it and find its equation later on. So anyway, let's begin by reminding you, so recall or reminder, that to find the equation of any line in general, you need something called the point slope formula. So what is the point slope formula? It's a formula that you probably came across at some point in maybe your algebra class, and it's basically this. It's y minus y1 equals to m times x minus x1. This is the formula that you use to find the equation of any line, regardless of whether it's secant, tangent, or in algebra or in calculus. This is always the starting point to find the equation of any line. So if you hear the words find, equation, line in the same sentence, this is where you have to start. And when you write it down, you have to ask yourself, am I given all of the things that I'm missing? So what we're missing are three things: an x1, an m, and also a y1. So x1 is the place where you want the tangent line. For me, x1 is given. It's this x equal to minus 1. And that's pretty much the only thing that's given to me. The other two things I need, m, which is the slope of the tangent line, is missing. We don't know it. They did not give it to us in the paragraph. And y1 is also missing. What is y1, by the way? It's the y-coordinate of the point that you want to find the tangent at. So in the calculus notation, m, that you're missing is the f prime of x1. And y1 is the f of the point that you're missing. So notice that the difference is very, very, very small. One of them has an apostrophe, and one of them does not have an apostrophe. And they both are doing completely different things. The f of x1 is finding the y-coordinate on the function f of x when x is equal to -1, whereas f prime is finding the slope of the tangent line to the function f of x when the point is -1. So those are completely different things. So make sure you know the difference and make sure you don't get them mixed up. And let's begin. So first, I want to know x1, and I'm going to say x1 is -1. This is given to us. We don't have to search for it. It's just right away available in the paragraph. They didn't put the subindex 1, but I know that's what it is. It's the number that's provided. Next, I will find f of x1, because that's usually the easier one of these two that are missing. And f of x1 is basically f of -1. So I just need to find what the y-coordinate is going to be when I put -1 into my equation for f of x. So put it into the equation of f of x, and you get -1 squared, and -1 squared is just simply equal to 1. So this is the y-coordinate when x is equal to 1. And finally, the complicated thing that you're here to learn, the f prime of x1. And by the way, I'm going to write m because I want to remind you that this is the slope of the tangent line at the x-coordinate. In this case, the x-coordinate is -1. So it's the f prime of -1. And how do you find it? You've got two different ways, either the limit with x approaching a or the limit with f of x, the limit with h approaching 0. I'm going to use the limit with h approaching 0. And so I'm supposed to write down f of a plus h. The a for me is -1. The h for me is just h. We don't know. It's just some random number. It's the distance that's approaching 0. Next, I'm supposed to write f of a, which for me, again, is -1. And I'm supposed to divide all this by h. So where did this come from? Where did this limit suddenly show up from? This is just a difference quotient. I'm going to rewind back and show you where it came from. It's basically this. Okay, I had a choice to make. I either can choose this definition or this definition, and I chose to go with the second one. That's my preferred one because it works better later on in future sections. Although the math might sound or feel a little bit complicated for the problem that we're dealing with, this is actually better for later on. So in any case, let's continue the process. So the m, which is the f prime of -1, consists of the limit as h approaches 0, and now I need to do a lot of things. Keep track of this minus. It's going to be in the middle. But first, I need to investigate what is f of -1 plus h. So what is it? It just basically means go to the function f of x and replace all the x's with -1 plus h. And when we do that, we just get -1 plus h squared. And that's the end. The minus sign that was in the middle is right there, in the middle again. And next, we need f of -1. That's literally what happens when you put -1 into that function. And we already know it's equal to 1. We already did it before, so we're just going to copy the answer. And it's all divided by h. So at this point, what you're supposed to do is FOIL everything, combine like terms, divide it out, and see what happens. So I'm going to write the limit as h approaches 0. And again, to FOIL this part, I'm going to use a formula. Or if you don't know the formula, you can just write -1 plus h times -1 plus h and FOIL it the traditional way. The formula I'm going to use allows me to get the answer really quickly. It's 1 minus 2h plus h squared. And then I have the -1 next. And that minus is now here at the end. Now, let me redo the problem real quick to show you that the FOIL procedure also gives the same answer. -1 times -1 will be +1. -1 times h will be -h. H times -1 is going to be -h again, and h times h is going to be h squared. And that's how I'm getting 1 minus 2h plus h squared, which is what I wrote here at the beginning. So regardless of whether you use the formula or you just do what I did here, you will get the same answer. So you know what? Since I already did it, I'm just going to keep it very, very small and write it kind of on the side so that people can kind of see where I got the numbers from. The denominator of this whole thing is just h, so let's not forget about that. Now, I don't know if you can see or not, but for me, it's pretty obvious that the 1 minus 1 should be canceled out because 1 minus 1 is 0. And also, the remaining terms will all have an h. So I'm going to factor the numerator. So again, all this work is to find the derivative, meaning the instantaneous rate of change or the slope of the tangent line. But that's how it works. So factoring the h out, I'm going to have h times -2 plus h on the numerator, and there's an h already in the denominator. So keep writing that h on the denominator, and hopefully you're seeing again that we need to cancel the h's because there's multiplication. We're allowed to do this. And what I end up with is a limit as h approaches 0 with -2 plus h. I know it is annoying to keep writing limit, 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 limit everywhere, but it's part of the process. If you don't write it, if you forget to write it and you get here and you put a box around this answer, your solution is going to be so off that you're probably not going to get some partial credit. So it's going to cost a few seconds to write it every time, so just make sure you keep writing it. And we keep writing it because once we have the answer already simplified like it is now, we will use direct substitution and say, well, h is approaching 0, let's put 0 there, and get the final answer. It's -2 plus 0, which is -2. So the slope we're looking for is -2. So the blue number that we're missing is -2. Now, let's put everything together and go back to this over here. So I'm going to grab the formula from the top of the page and say, finally, after all this work, y minus y1 equals to m times x minus x1 becomes, with all the numbers plugged in, it becomes y minus y1, which is 1. That's the green number, by the way. So let me color it in green. It's equal to m, which is -2. That's the blue number that we just found. And it's multiplied by x minus x1. And x1 itself is negative amount. So be careful. You need double negatives because the formula already has a minus sign. And your x1 itself is also negative. So that's the equation of the line. I want to be able to put it in the calculator in a second. So let me rewrite this answer a little bit differently so that I can plug it into the calculator. In order to plug it in the calculator, I need to have the letter y all by itself. So let's just first kind of clean up the right-hand side. It's -2. The double negatives becomes positive, so x plus 1. And then I can multiply the -2 times x. I can multiply the -2 times 1. And I'm going to move this -1 across the other side, so I get +1 instead. And so the final answer is -2 x minus 1. And the reason why I'm doing all this is because I want to show you the picture on the calculator so you kind of see what we just did and what we produced, basically. You should be proud of yourself. This is a huge milestone. This is the first time you're doing derivatives and probably the first time you find the equation of a tangent line. This is hundreds of years old question that people were trying to answer, and now you know how to answer it too. So to kind of see what's going on, let's go to our calculator, and I'm going to go to my y menu, and let's write x squared, the name of the function that we're working with. And next, what I'm going to do is put the equation of the line that we just found, and the equation was -2x minus 1. We just finally discovered it, so I'm going to put -2x minus 1 there. and I'm going to reset my zoom to the standard zoom, and there it is. So we have a parabola, and we have a point called x equal to -1. By the way, this is the point. And notice that at that location, doesn't matter if you're standing at the parabola or at the line, the y coordinates will be the same. It's getting us y equal to 1 when we're on the parabola, and when we jump to the curve and go to -1, the y coordinate is also equal to 1. So that's what we want to see. Let me zoom in on that location real quick. I'm going to go from -2 to 0 on the x-axis. And if I click graph right now, you'll see it does not look terribly good. So I want to make this a little bit smaller as well. I think a good window for the y should be somewhere from -1, let's say, to +2 on the y maximum. I think this will put it smack in the middle of the screen. And there it is. So again, if I trace -1, that's the location we care about. So the red line and the blue curve are tangent at that location, meaning the red line is only touching the curve at that one spot when x is equal to -1, and its slope we discovered was negative. So that's pretty cool. And before I close the calculator, I want to show you a cool feature that the calculator has. And this is the first time we're going to be using it. So what I want you to do is to click on the second key, then click on the key that's called trace, and that opens up a calculate menu. It's a hidden menu. You have to always click second to access it. In this menu, there's a bunch of numbers or a bunch of options. But what I want to go down to now is option number 6. And this is the notation that we'll be using later on for derivative at a point. So it's dy divided by dx. I want you to select that and then click on your keyboard -1 and then hit enter. And you'll see now on the bottom of the screen on the calculator, there's two lines, and the first one is dy over dx equals to -2. And what the calculator is basically confirming is it's telling us that on the blue curve, because all my writing here is in blue, on the blue curve, which is the x squared parabola, the slope when x is equal to -1 is -2. So the dy over dx is the name of the slope, basically. This is the notation we're going to use later on, but it's just a little preview into the future. The slope is -2, and the x coordinate is -1. The y coordinate is also equal to 1. So the calculator can do this, by the way, whether you have the red line or not already drawn. And just make sure that when you select this option, you're standing on the parabola. So again, starting from scratch, what you're going to do is you're going to go to the Y menu, and you're going to pretend like we don't have a line. We just have a parabola. So here it is. And then you graphed it, and now you're looking, oh, okay, cool parabola. I want to know the slope at -1. So you just click second, and then the trace key, and you go down to option number 6, which is the slope command. You hit enter, and then you tell the calculator where you want to find the slope. So I'm going to select -1, and I'm going to hit enter, and the bottom of the screen will tell me the slope is -2. Obviously, if I select a different location, so if I select option number 6 again and click -1.5, for instance, the slope is going to be different. Because it's a different location, the tangent line is going to be completely different, and the slope in that location is apparently -3. Cool. Well, that's about it for this problem. I think we have really talked about it a lot. And the last thing we're going to do is discuss example number 7, which is more practice doing the same things. Okay, so let's begin by reading the question in number 7. So the profit earned by a company in thousands of dollars that manufactures X hundreds of widgets is given by the function p of x equals to -x squared plus 30x minus 100. So the first thing I'm going to note is that it says x is the hundreds of widgets. So if I want to plug in x equal to 100, if I want to know what the profit is for making 100 units, I can't plug in 100 into this formula. I need to plug in actually just 1 if I want to know what is the profit for making 100 widgets. So that's what they're saying over here. I got to pay special attention to that. So later on, we're going to be dealing with 300 and 500. So that means we're going to be putting 3 and 5 into the formula, not 300 and 500. So that's the first thing we need to be careful about reading the question. But anyway, in this problem, we're going to be basically summarizing everything we did so far in this section. So it's both finding the average rate of change in the first part of the problem and then finding the instantaneous rate of change in the second part of the problem. Well, we begin with the first one. It says find the average rate of change and the profit if the company increases the widget manufacturing from 300 to 500. So I'm looking for the average rate of change. And as usual, I'm going to write the formula, not using algebra notation, but using calculus notation. So remember, we said x is in hundreds of widgets. So for this one, x will be 3. And for the second one, x will be 5. So I want to know the profits rate of change if I go from 300 to 500. So we'll start with p of 5 minus p of 3, and we'll divide by 5 minus 3. Okay, why am I putting 5 not 500 and 3 not 300? Again, that's because of this wording that's found in the first paragraph. X represents hundreds of widgets. So anyway, now I want to know what I get when I put 5 into this equation. And you can do that by hand. You can put negative 5 squared plus 30 times 5 minus 10, and then calculate everything by hand. It's not going to be terribly difficult, but we have access to calculators, so we're going to take advantage of that and just use the calculator to find the answer. So in this case, I'm going to start with the negative 5 and then square it. Then I'll put the 30 times 5. Then I'll subtract the 10 at the end, and that's going to give me 115. The second one, I need to plug in basically 3. So let's see, I'm going to go again, negative 3 squared plus 30 times 3, and then subtract 10 from that. So 115 minus 71 is my numerator. So let's write down 115 minus 71. And the denominator is obviously going to be 2 because 5 minus 3 is 2. So remember, this 115 represents the P of 5, and the 71 represents the profit of making 300 widgets. So now, again, I'll just need the calculator one more time to find the complete answer. So let's do this here, 115 minus 71, surrounded with parentheses, divided all by 2, and it turns out to be 22. So 22 is the final answer, and I'll let you worry about the units in case you want to put them or not. It's in thousands of dollars per hundreds of widgets. I'm not going to write that here, but that's what it is. Anyway, that's the end of the rate of change. So cool, we're done with that part. That's the easy part. And now we are looking for the instantaneous rate of change, meaning the derivative or the slope of the tangent line when the profit is 25. So again, we know the x, but we need to decide whether we want to use definition number 1 or definition number 2. So it's up to you. So in this particular instant, I think I'll go ahead and find the answer, p prime of 25, that's the instantaneous rate of change, using the first definition. So it's the limit as x approaches a, and in this problem, a is the number I care about, which is 25. Then I'm supposed to write f of x, or instead of f in this problem, I should be writing p of x minus p of a, which in this case is 25 again, all divided by x minus a. And again, a is the number 25. So you've got two choices, either the limit definition with the x or the limit definition with the h. It's your call. You pick whichever one makes more sense to you. Since I did already a problem with h's, let's do this problem with the x's. So anyway, this is the limit as x approaches 25. And first things first, I'm supposed to write the p of x. P of x is the function itself, so I'm just going to copy it down. Negative x squared plus 30x minus 10. So that's what I get for finding p of x. Actually, I didn't find it. It was just given to me. I just had to copy it down. And there's minus sign next, so I gotta be careful, put minus next. And then p of 25. So I'm supposed to put 25 into that equation. And it's going to be complicated, so again, I think I'll opt to use the calculator to find it. So let's go to our calculator and plug in 25. So I will do minus, and then the 25 inside parentheses squared. Then I'll need to multiply 30 by 25 and subtract 10 from everything. Okay, so I'm getting 115, which is cool. So that's the number that goes next. So 115 is next, and that replaces the P of 25, and it's all divided by x minus 25. That's the denominator. Okay, not much to do on the numerator except clean up the little mess that we've created. And so again, I'm looking for P prime of 25, or the slope of the tangent line, or the instantaneous rate of change. So first, I'm going to write negative x squared plus the 30x. And let's just do this mentally. There's a negative 10 and there's a negative 115 next to it. The total is going to be negative 125. And so let's just factor it right away and divide it all by x minus 25. Okay, so what I need to do next is basically factor the numerator. So let's go to a scratch paper first and write the numerator. So it's negative x squared plus the 30x minus 125. And I really don't like that my leading guy has a negative sign, so I'm going to first start by taking out a negative 1. That leaves me with x squared, and it makes the 30 negative, and it makes the 125 positive. So it's a little bit better to do it this way because we don't like having a leading coefficient that's negative. Now, to factor the inner portion, I'm going to use the big X method. I'm looking for two numbers that when you multiply, you get 125, and when you add them, you get negative 30. And I think negative 5 and negative 25 will get the job done because when you multiply them, the answer is going to be 125, and when you add them, you get negative 30. So the solution so far is negative 1 times x minus 5 and then x minus 25. So those are the numbers that we just found using that like big X method or the sum product methods, right? And that is what should be placed in the numerator. So p prime of 25 is the limit as x approaches 25. And now my numerator is going to have negative 1, and then x minus 5, and then x minus 25, all divided by x minus 25 again. And I'm doing all this so you can see that the x minus 25 can be reduced to lowest terms. So far, my p prime, the instantaneous rate of change, is the limit as x approaches 25 with negative 1 times x minus 5. So if I didn't have the word limit written down on every line, I would forget what I'm doing and I would put a box around this answer, and that would be completely wrong. What I'm supposed to do now is take the x, which is approaching 25, and plug it in. So use direct substitution, and let's see if it works. And obviously, it's going to work in this case. So I'm going to end up with negative 1 times 25 minus 5, which is negative 1 times basically 20. So the total is negative 20. So the slope of the tangent line when x is equal to 25 is actually negative 20. I also added the unit, which is thousands of dollars per hundreds of widgets. So the slope is negative, and there's actually a follow-up question here, which is should the company increase or decrease production? And they're telling me to look at the graph. But right off the bat, I'm seeing that the answer here is negative, and that's bad news. That means they're losing money when they're making this many widgets. So they should probably increase or decrease. Let's look at the graph to decide. So which graph are we looking at? We're looking at the graph of the function that's provided. So let's go to our calculator again. This time we're going to go into the y menu and type in the function that we were given, which is negative x squared plus 30x, negative x squared plus 30x, and then minus the 10. And let's go to the zoom and click 6. That will give us a standard zoom, and we can't see the full graph. I'm expecting a parabola because of the square that I typed in, and I'm not seeing that here. And obviously, I want to know what's going on, so I need to modify my windows a little bit. So the standard window did not work, so we've got two ways to deal with it. Either manually modify the window, or if you click on zoom, you can tell the calculator to find the best option by choosing zoom fit, which is option number 0. So let's try that one out first and see what the calculator gives us. I think that might work, but let's see. So if I click zoom fit, I'm still kind of seeing a portion of the graph. Remember, I'm trying to figure out what's going on at x equal to 25, and the screen right now goes all the way up to 10, basically, right? So the maximum here is 10, and that's not good. So I want to go to the window myself and change some stuff. So first, I don't need to know what's happening when I make negative widgets. That's not a thing. So I'm going to start with x minimum being 0. I am interested in what's happening at 25, so I'm not going to stop at 25 for my x max. I'm going to go maybe up to 40 or even 50. So let's see what happens so far. If I click on graph, you see we're seeing kind of a parabola. It's missing the top portion. I don't need to see all the stuff below the x-axis, so I'm going to go ahead and remove it, and I want to see more of the top of the parabola. So to fix that, I'm going to go to my y minimum, make it a 0 because I don't care to see negative y's, but I want to see more positive y's. 190 seemed like it's not enough, so let's go with 250 and see what that gives us. So here's the parabola. It took a little while to see it on the screen, and those skills are things you want to be able to develop on your own too. And so now let's click on trace and go to 25. That's the point we're interested in. And so you can see the parabola is on the way down there. And as a matter of fact, if I click on second trace and use option number 6, I can find the slope at that location. It's negative 20, just like we found on the paper. And yeah, so what should happen? If I move to the left and right of it, if I trace, for example, 20, you can see that the slope there is negative 10. If I trace, for example, if I go back to calculate the slope at, let's say, instead of 20, I go 15, you can see that the profit there is 0. So the slope, the slope is equal to 0. So it seems like it's a better idea for the company to stop production or decrease it, because if they continue going on this curve, it's not good news for them. Their slope is basically, we're seeing that their slope is negative, so they're losing money, right? The graph is kind of going downhill from the vertex down. So the answer, should they increase or decrease the production? I would tell them decrease your production and you'll make more money. If you keep pumping this many widgets, 2,500 widgets, you're going to profit less than if you make, let's say, 2,000 widgets or even fewer than that.